We've finally arrived at the moment to do organic synthesis. Yes. Synthesis. In your synthesis on your test, you're going to start with acetylene. Remember that's called acetylene, also known as ethine. And we did this exercise already. I need a base that lets me take the H off of an acetylene. And somebody said hydroxide by mistake. And I said, I can't give you credit for that. And we did TKEQ and figured out why. Hydroxide doesn't give any product. It stays unreacted. So we had 4 other bases that we did in an activity on Monday. Give me one of them. Hydride, good choice. In fact, I will take that as an answer. You do not need a spectator ion ever for me. You can write H minus. That works. Might use H minus every time you want to take the H off of an alkyne. Not any alkyne. An alkyne at the end of a chain called what? A terminal alkyne. And this is actually part of this activity. Terminal. Terminal. And this is the only one that is in the middle, right? Internal. I think it's pretty self-evident why those names exist, right? Terminal at the end of the chain, internal in the middle. Now, an activity we didn't, or something we didn't discuss, and I'm going to show you the mechanism here, even though it wasn't asked for. That's a C minus. And you need a carbon that's got a halogen on it, bromine, chlorine, or iodine. And 2 more carbons here, because there's 3 carbons here, 3 carbons here. Okay? And what happens is, and if you had to describe this, what kind of description would you say when you come in from there and this thing leaves from the other side? You have a name for that? That is another backside attack. Backside attack won't work unless you have a halogen there. You need something that leaves. It's got to be stable, leaving. So remember that. If I want a new bond, I need a C minus from an alkyne, and I need a carbon with a halogen on it. Chlorine or bromine, just stick with those 2. Just make your life simple. Okay? There's other versions available. We'll learn about those later. And that is your first synthesis right there. This is a new bond, isn't it? I don't want to erase it. That bond there's new. And making new carbon-carbon bonds is called what? Sure. Uh-oh. That won't help.
No, I can take that.
Making new carbon-carbon bonds is called what? Synthesis. So we're supposed to outline, put a star in each step that qualifies as a synthesis. Well, that gets a star right there. This step right here. Boom. I like it. And we'll do one more synthesis very soon, but it's the same as the first one. Now, previous activity. We had a reaction that took a terminal alkyne and made it into an aldehyde. And we had a different reaction that took a terminal alkyne and made it into a ketone. What chemicals did the ketone? That was our second activity today. There's 3 of them. Just remember, there's 3 chemicals for either one of these. Mercury, sulfate. 2 more chemicals, please. The oxygen comes from water. And sulfuric acid gets rid of the mercury. It's called protonolysis. That's how you get a ketone from a terminal alkyne. How about the aldehyde? That was activity 3 today. This one's a two-stepper. First step, hydroboration, HB with 2-sia. I never explained sia. Sec, iso, amyl. Same as sec, iso, pentyl. Amyl and pentyl, synonymous. So that's hydroboration. Step 2 is oxidation. What's your oxidizing chemical? Water's not going to help. Peroxide, H2O2, and you got to do that acid-base reaction in the first step. You better have a base. Hydroxide. So I know how to make aldehydes, and I know how to make ketones. Okay. Hey, what about the reagents to make a terminal alkyne into its conjugate base, which is this thing? It's been done already today. What chemical lets us take the H off of a terminal alkyne and make it into an anion? It's conjugate base. It's already on the screen. Yeah, what's the strong base we used before? Because we can use it again. OH minus gets 0 points. It's not strong enough. We tried that last Monday. We did the pKa's, didn't work. SO42 minus is not that good of a base either. Guys, we had 4 really strong bases. We've used one of them today. H minus. There you go. H minus takes the H off a terminal alkyne. You might want to review the other 3 from Monday as well. Okay? There was the conjugate base of an alkane. There was the conjugate base of an alkene. There was the conjugate base of an amine. And then this was the 4th one, H minus. And it's time to do what? This carbon's going to end up with a new bond to carbon. What's that called? Synthesis. What chemicals needed? 2. There's 2. You need the conjugate base of an alkyne. We've got it already. What's the other chemical that reacted with the conjugate base of this alkyne to make this product with this new sigma bond? I needed a carbon with a halogen. And how did I know I needed 3 carbons? How did I know that? There's 3 new carbons there. How many new carbons do I need this time? They're up here. 2. I need a bromine attached to an ethyl. Bromine, ethyl. Okay, I got stuck with bromine. Could be chlorine. Could be bromine. Could be other options you learn about in chapter 9, but we're not there yet. And these 2 reactions over here are our final new reactions for this test. I'll do a mini lecture down here for reductions of alkynes. A summary of all the reductions you're responsible for. And we'll just deal with internal, R1, R2. We need to be able to make it into trans. We need to be able to make it into cis. We don't really need this reaction, but we have to avoid it. Oh man, that's a money-losing reaction. What do I mean? You took something valuable and made it onto something less valuable. I really like the dollar sign here. I don't know why. They're even in the book. Double bonds with geometry are very valuable. That's what I'm trying to say with $3. Alkynes that are internal are fairly valuable. You had to do some synthesis to get there. That's $1. Alkanes, we literally dig out of the ground. Let's not make them. They're already found in the ground. It's called crude oil. Okay? So please don't use useful molecules to make them into stuff that we can dig out of the ground. And that reaction is one you know. H2 with a catalyst. Does anybody remember the catalyst? We only mentioned it briefly once, last Wednesday, I believe. Or 2 Wednesdays ago, sorry. Platinum, yes, thank you. I forgot we had a break last week. H2PT. So you think H2 would work here, and it doesn't. If you put H2 in PT, it's clearly wrong. So there was many chemists that researched this, and they played with different catalysts. They needed to find one that would only react with the alkyne and not the alkene that you make in the first step. Because the first step in this reaction is to make an alkene, but then the alkene immediately reacts. And it's kind of an interesting story. They tried all the catalysts that were less reactive than platinum, and they couldn't get them to work. So they ended up trying this strategy. Well, let's take a catalyst that starts out more reactive and add something that kind of turns down the volume on it. It's called a poison. So it's like a wounded catalyst. So they take palladium and they use lead sulfate. That's a poison, lead 2 sulfate. And the palladium is embedded on chalk dust. We don't use chalk in this room. You've seen chalk, right? Do you know what chemical chalk is? It's the same chemical that is the egg shell. Oh, we don't know the chemical that's the eggshell? No, calcium carbonate. So basically, that's a support. It's like the powder that the catalyst sits on top of. And this combination down here is called Lindlar's catalyst. On a test, if you replace what's in that box with the words Lindlar's catalyst, the only way you get points is if you spell it 100% correct. It's already a guy's name. I don't like that to start with. Okay? If you make any mistake in his name, 0. So don't. Why don't you try the 3 chemicals, and at least you get partial credit if you don't get them all right. Okay? And on tests, I'll see if this was a reaction box, like tell me what to put in this box. I'll tell you the #1 mistake. The student puts Lindlar's catalyst, they spell it right and they want full credit. They didn't put H2. That's the chemical that makes this thing happen. I can give you at best half credit, okay? H2 is not part of Lindlar's catalyst. You have to throw in the catalyst and bubble in hydrogen from a tank. That's 2 separate things, people. Please remember that, okay? Lindlar's catalyst is what's in the pink box. All right. That's one way to make CIT. Alternate to H2, Lindlar's catalyst. You can use this combination. BH3 and acetic acid. Borane and acetic acid. I think we will do an activity 6 at the end because I forgot to do that mechanism. We will do it. So we have 2 ways to make CIT. H2 with Lindlar's catalyst, or BH3 and acetic acid. That could be, you know, in the red box. And the trans will be part of that activity as well. Na, NH3. That's two separate things. That's a Na you can't cross off. Why not? Say it again. No, it's not an ion. That's why I can't cross it off. It's an element. And when you're done, it's not an element. Now you can cross it off. But there was a reaction that made it from Na methyl, that's what Na is, Na methyl, into sodium ion, which is right here. That's oxidation. Okay. So you have to know the chemical that makes a transalkene, the chemical from an internal alkyne. Just a reminder, internal alkyne can be made into a trans or a cis alkene or an alkane, but I'm never going to ask you how to do that because it's a waste of time. So you think you're ready for your box now based on the information we've learned? This one up here, cis or trans? Yeah, trans. You have to give me sodium and ammonia. You can go Na, comma, NH3. You can go Na over NH3. You cannot do this. Yet every semester I see a student invent this unicorn. That is a unicorn. It's not a chemical that exists. NH3 has no charge. What are you doing putting a sodium in front of it? Okay? That is not the right answer. This is the first semester ever when no one gives that answer. Promise me, please. Okay. You can give me the answer like this, where they're clearly separate, or here, where they're separated by a comma. Okay, I go on about little things. I'm sorry. There's two possible answers to go from an internal alkyne to a cis alkene. They're down here. Why don't you do the one that's harder to mess up with? Isn't that harder to mess up with? Why not? BH3, CH3, CO2H. Okay. That's the end of that story. You don't really need the reductions of alkynes notes as part of your activity. And we're going to jump right to the next activity anyway, okay?